Okay, in this video, we're looking at electrode potentials, electrochemical cells. It's a little different to the other video I did on this topic, which is one of the reasons why I'm doing the second one. That's partly because we're focusing first on the fact that we actually have some, we have a table of data. So all of this data that we have here, this table of data, is before there are any questions. So the questions don't start until after that table, which means the information in the table could feature in any of the questions that follows, or could be relevant to any of the questions that follows. So let's just take a little time, first of all, to be confident that we understand what this data, I guess, is showing us. So you'll notice that all of the half equations are written in the same way. They've got the oxidized species on the left and the reduced species on the right. So when we look at the equations from right to left, from left to right, apologies, reduction is taking place, which means if we flipped the equations and we went from right to left, then we would have oxidation happening. So from left to right, it's reduction because we can see that a species is gaining electrons. So we have a gain of electrons. We have an oxidation number, say, on that first one of 0 because it's an element, and we have -1 on the right, so we can see it's being reduced. Okay. Now, if something is being reduced, then that means it can act as an oxidizing agent. So that means all of the species on the left have the potential to act as oxidizing agents. Because if they're being reduced, then something else must be being oxidized. You can't have one without the other. Similarly, if we look at if we started on the right-hand side, so if we went from chloride to chlorine, then the chloride is being oxidized, which means that anything on the right could act as a reducing agent. And that's going to be important or helpful to answer a question in a bit. Okay, so I think that's probably enough for us to start with at the moment, just to get a sense of this table. The other thing to notice, and this isn't always the case, so please be careful, but we do actually have the table is in order of values, so we have the most positive at the top and the most negative at the bottom. This isn't always how they present the information, so just be a little bit careful about that. But we've got most positive and we've got most negative, or least or least positive. All right, the first question is really a year 12 question because it's asking us to work out the oxidation state of nitrogen and in NO3- or nitrate, and in NO. So hopefully this is a fairly straightforward question. So what we don't know is nitrogen, so I'll let that equal Y. Oxygen is always -2, or each oxygen is worth -2, unless it's bonded to something more electronegative than itself, which can only be fluorine. So in which case oxygen would have a positive value, or if it's in H2O2, hydrogen peroxide. But otherwise, it's always -2, and there are 3 of them. Okay, so we've got Y, which we don't know. We've got +3 -2, which is going to obviously be -6, and then what it equals is whatever the charge is, which in this case is -1. So what we're saying here is we're saying that Y -6 equals -1. So therefore Y, and we add 6 to both sides, Y must equal +5. So in the nitrate, we have an oxidation state of +5. And we use the same principle with nitrogen monoxide. Nitrogen is what we're trying to work out. There's only one oxygen, which is -2, and then there is no overall charge. So we've got y -2 equals 0. So y must equal 2. Okay, so hopefully a fairly straightforward question, really, in the grand scheme of things. The next question asks for the weakest reducing agent in table 4. So if it's a reducing agent, it's going to be something on the right-hand side of the half equation. So only what features on to the right of the arrow can be a possible answer. Now, how can we work out which it is? So a useful mnemonic, and of course you've got to understand how to use it, but a useful mnemonic is pioneer. And what that stands for is positive is oxidizing, and we're talking about agents here, and negative is reducing. So the way to read it is the most positive electrode, the half cell electrode potential here will give you, the most positive will give you the most powerful oxidizing agent, and the most negative will give you the most powerful reducing agent. So if we were looking at the most powerful reducing agent, we would look at the most negative value, which is minus 0.44. It has to be on the right-hand side of the half equation. So our most powerful reducing agent would be iron in this table. But it's asking for the weakest. So the weakest here is going to be the most positive value. And it has to be the right-hand side. So it's going to be the chloride ion. So I will just go through that again, just to make sure that you're happy. So this is why we started with the table and thinking about what could we think about just even by looking at the table, knowing that from left to right is reduction, from right to left is oxidation. If something is being reduced, then it can act as it is acting as an oxidizing agent. If something is being oxidized, it is acting as a reducing agent. That means we know where the possible oxidizing agents can be, which is they have to be on the left-hand side of these half equations, and any possible reducing agents must be on the right-hand side. And then this useful sort of mnemonic, the most positive electrode potential is going to give us the most powerful oxidizing agent. So this is the most positive. So our most powerful oxidizing agent here would be chlorine. And the most negative is going to give us the most powerful reducing agent. In this table, minus 0.44 is the most negative value. So iron would be the most powerful reducing agent. And of course, if we're talking about the weakest is going to be, in the case of reducing agent, it's going to be the most positive value, which is here, and it's going to be a chloride ion. It still has to be from the right-hand side because we're talking about a reducing agent. Then it asks us to write the conventional cell representation that has the EMF of 0.43 or plus 0.43. Now, the 0.43 is the difference between them. And so another way to think, they have been very kind in giving us these values in an order, because really you can think of this as a number line, okay? So we've got a number line where that is 0, that is minus 0.44, that's plus 0.17, and so on, okay? So to get a value of 0.43, then we have got to have a difference on our number line of 0.43, and obviously I've already thought about this, but we have that here. So the difference between 0.77 and 0.34 is 0.43. Now, when it comes to writing our cell diagram, given that we have an overall electrode potential of 0.43, that means it's done as it should be, which means that the right-hand cell must be the most positive. So that means this So the most positive is the right-hand cell. The only exception to that, or the only exception that there could be, is if you had a standard hydrogen electrode, in which case that is always the left-hand cell. So our most positive is our right, and our most negative, or least positive, is our left-hand cell. So when we write this conventional cell diagram, we've got to bear that in mind. So we're going to have the copper on the left and the iron on the right. And when you come to write conventional cell diagrams, you write them in the order of reduced species, oxidized species. This is for a half cell. Then we have the salt bridge. We'll come to the phase barriers in a second. And then we have oxidized and then reduced. That's just in terms of the order. Okay, so let's go back. Our left-hand cell is the one with copper. We start with the reduced species, and the reduced species is the copper solid. We have to start any cell diagram with a solid, and we fortunately have the actual metal that's being oxidized here. But if we didn't, if we had, I don't know, we had a gas or an aqueous ion being oxidized, then we would need to make sure that we had a platinum solid electrode. But we do have copper. Sorry, I seem to be picking the wrong here. So we've got copper. I'm going to put the state symbol because I think for our understanding that's important. AQA tend not to really care about the state symbols, but I think they are useful for your sort of understanding it. So that's our reduced species. Our oxidized species is copper 2+, and that is aqueous. And because they are different phases, there's a boundary between them. We have to put our sort of vertical straight line there. So that's the left-hand half cell. Then we're going to have our salt bridge, which we represent with the double lines. Then we're going to have the oxidized species and then the reduced species. So if we go back to look at the other half equation, we'll notice that we've got our most oxidized species is Fe3+, and our most reduced species is Fe2+, and they are both aqueous. So there isn't a phase boundary. So we're going to have Fe3+, aqueous, and because they are in the same phase, we separate them using a comma. But we've still got to write them in the correct order, though. We're still writing oxidized and then reduced. Okay, so that's very important. And then now this is an example where we don't have now yet a solid at the end. So what we've got to make sure, we've got to have an electrode, and so we're going to put our platinum electrode. So a few things just to say about that. So I'm just going to rub out this and then put that above. So there's our reduced species, and then our oxidized species, and then our oxidized species, and then our reduced. One thing I will also say is that if the order of the overall reaction is from left to right, so what that means is we would have copper on the left-hand side and Fe3+ on the left-hand side, and they would be added together to produce copper 2+ and Fe2+, and of course we'd have to have a balanced equation. But when you combine the two half equations, that would be the direction of the reaction. Copper would be being oxidized and Fe3+ would be being reduced. So just to add a couple of details, just to remind you about a few things. So the Fe3+ and the Fe2+ are in the same phase. So we separate with a comma. I'll just say here different phases. One's a solid, one's aqueous. So we separate them with a line. Now, some people explain phase as being state of matter, but that's not strictly true. It can be a way to help you think about it. But really, a separate phase means that there's a boundary between them. So if I added oil to water, they would both be liquids, but as they don't mix, if you think about the fact there would be two layers, there would actually be a boundary between them, and so they would be different phases in that respect. But you know, thinking of them as states of matter isn't bad. Don't ever explain it that way, but you're never going to be asked to explain it anyway. You really just need to use it. So there's our conventional cell representation for getting plus 0.43. So this is a good question for us to go through. So it says use the table or use the data from table 4 to identify an acid that will oxidize copper. So what does that mean? If copper is being oxidized, then that must be the more negative half cell, which means that the acid must be more positive because the acid's being reduced. Okay, first thing to say. So we've got to explain our choice of acid, use these data to suggest a possible equation for the reaction, calculate the EMF of the cell that has the same overall reaction. So because copper is being oxidized, we know it must be the more negative half cell. If we go back, we can see that copper is here. That must be more negative than whatever else we're going to look at. So instantly, it rules out what's below. Okay. So what it's ruled out in this respect is it's ruled out sulfuric acid. So because copper is being oxidized, we must have something else that's being reduced. We must have something that is more positive than this half cell. So when we look above, there is only one acid above. There's only one half equation that features H plus ions, so protons. That is this one here. And if we look at it and we look at what the other species in that half equation is, it's the nitrate ion. So this must be nitric acid. So, I mean, it really boils down to you appreciating this. This is absolutely critical to answering this question. So for 1 mark, our acid is nitric acid. So what I'm also going to do is I need you to appreciate, that we're answering a series of questions. So this is the first question, which we've just answered. We've got to explain it, and then we've got to use the data to have an overall equation, and then we've got to calculate an EMF. This is quite a lot actually for 4 marks. Now the way that AQA, so now we're going to explain why, or justification for that nitric acid. The way that AQA present these, the way they present these things in mark schemes is they represent a half cell value by drawing them as those sort of fractions. So what they would write is they would have something like that. So it's the electrode potential for the nitrate, and what you do is you write the oxidized over the reduced species. So you have to look at the half equation, and when you look at this, you have to identify what's being reduced as you go from left to right. It's not the hydrogen because it's +1 there, but it would be also +1 in the water. We were asked at the start of the question for the oxidation numbers of nitrogen here, so we had +5 and we had +2, so we can see that's reduction, right? So you always write it as the oxidized, the left-hand species over the right, And then we're saying here that when we put this greater sign, that we're saying that it's more positive than the other electrode half cell potential that we're looking at, which is the copper, which again we write the 2 plus over the copper. So again, the oxidized over the reduced. If you write it like that, and you just want an idea, get a sense in your head about what's happening, the more positive is where reduction takes place, and the more negative is where oxidation takes place. So this would be the overall reaction. Now those arrows are not part of the mark, right? Those arrows are not part of something that would be expected in the mark scheme. We're simply saying that the nitrate half cell is more positive than the copper half cell. Okay, now we need to come up with an overall reaction equation. Now, the simplest way to do this, although it's a little bit, or the safest way, sorry, not the simplest way, the safest way to do this, it's a little bit long-winded, is to write the half equations. So, and then to add them together. So we've got the half equation, equation for 1. So we'll do the nitrate. So it's being reduced. So NO3 minus plus 4H plus 3 minus. So don't forget, in the exam you would have the table of data on the left-hand side of the page. You would be able to read this very easily. So you have to just trust me for the moment that I'm copying this out correctly, especially as I made a mistake there. And the other half equation is copper goes to copper 2 plus 2E minus. And when we add half equations together, we have to make sure that the electrons cancel out. So we've currently got 3 on the left and 2 on the right. So we're going to multiply the top one by 2 and the bottom one by 3. So just put that line underneath there. I suppose I should have didn't need to write this. I should have just ignored that. Add them together. So don't forget, we're multiplying the top by 2. So we're going to have 2NO3 minus plus 8H plus 6E minus plus the copper, plus 3 coppers, sorry, because I've times that by 3, goes to 2 nitrogen monoxides, 4 waters, 3 copper ions, and 6 electrons. Only the electrons cancel out here. So when we look at the overall equation, it is 2NO3 minus plus 8H plus 3Cu goes to 2NO plus 4H2O plus 3Cu2 plus. Okay, not quite finished. The final question asked us to calculate the EMF of the cell that has the same overall reaction. So let's just make it clear that we're answering that fourth question. So we have got E total equals E right minus E left. And E right is the more positive of the two. So when we look back at the table, and these are the two half equations. So it's going to E right is plus 0.96, E left is plus 0.34. So just going back and do that. Sorry. So plus 0.96 minus plus 0.34 equals 0.62V. So I hope going through that question has been useful. I hope it's been helpful to sort of be reminded about some of the principles about electropotentials. And I hope the video, I hope it's been helpful.